Today we're going to be talking about Lahars on Mount Rainier, and in particular how to calculate their physical characteristics. That is, how large they are, how fast they travel, and very importantly, how much time before Lahars that are generated near the top of Mount Rainier reach the town of Orting. Now, the town of Orting has a geological history of Lahars having hit it, and we know from that geological history that the principal hazard comes from either Lahars that come down and flow along the path of the Carbon River and reach the town, or that start up the top and go down one of these branches of the Puyallup River, eventually also reaching the town. So today we're going to want to look at how we can analyze the Lahar hazard at Orting, specifically by looking at how they come down the mountainside. And very importantly, we want to know the physical characteristics, how fast they travel and how large they will be. So to do that, we're going to look at the details of the topography in the vicinity of Orting and Mount Rainier. And what we see is that from the top of the volcano here, we have a path that comes down along the Carbon River through Carbonado and eventually reaches Orting. Or we have paths that come along various branches of the Puyallup River, go through this canyon, and then eventually also reach Orting. The Lahars are going to travel at different speeds depending on their steepness of the slope. The steeper the slope, the faster the Lahar. So what we're going to want to do is develop the appropriate equations that will allow us to actually calculate not just simply a general view of how they'll get there, but specifically what the timing will be, because we want to be able to decide where to install sensors, very similar to what we saw in New Zealand, so perhaps somewhere up high on the mountain, and knowing where those sensors should be, and then how much warning time they would give us before a Lahar reaches the town of Orting. So our job today is to determine how Lahars actually flow down the valley, and in particular, what are the equations we can use to put real numbers on that. So to do that, we're going to look at the behavior of Lahars and ask a couple of key questions. The first question is, how long will it take for the Lahar to reach Orting? And then once we know that, we may also be interested in saying something about how big will that Lahar also be. So to do that, we will look at a couple of things. We have knowledge that Lahars are driven by gravity. They will go faster down steep slopes and slower down flat slopes. And there are a couple of equations we can work with that are used to derive the behavior. Essentially, there are two equations. One is what we would call a conservation of mass. And conservation of mass simply says that if you push stuff down a stream, the more stuff you push down, that'll either make the Lahar get higher, or it will have to travel faster, and there will be some trade-off between those two. And that's written this way: dH dt, that is the change in the height of the Lahar as a function of time, will be equal to minus dq dx. And here we have h is the height, t is equal to time, q is equal to the flux, that is the rate at which the material is coming down the mountain, the Lahar material. So that's essentially a volume speed, and x is your position, and x will be with respect to the top of the mountain. And so with that approach, we have this equation that basically says that as the flux changes with position, the height will change over time. One other thing that we see here is that there's a minus sign. That minus sign is simply there because position x is measured from the top of the mountain down. So when we are looking back up the mountain to see what's coming at us, we're looking in the negative direction. But so this first equation, and this is equation 1 in the handout, is a relationship between the height of the Lahar and the amount of material coming down. We want to check they have the same units. The left-hand side, the height will be in meters, the time will be in seconds. The right-hand side, flux is going to be in meters squared per second, and the distance is going to be in meters, and so meters squared per second divided by meters is also meters per second. So one of the things we always like to try with math equations is that the units actually work, and in this case they do. So with that, we now can go on to the second equation, and the second equation is one that is built on how things actually flow, and this rate is also related to the flux as we had before, and this equation says that the flux is equal to a constant, which we'll talk about in a second, the Chezy constant, times the slope of the surface it's flowing on, in this case the slope of the mountain, that will be raised to the power m, and times the height of the Lahar, the thickness of the Lahar, raised to the power k, and this is equation 2 on the handouts. So in this case, Q again is our flux, but a couple of important parameters. C is what's called the Chezy C, and it is a measure of the roughness, the characteristics of the channel through which the lava will flow. So this is something that has been developed. It was originally developed when they were building the sewers of Paris in several hundred years ago, but it's an engineering constant that helps take into account things like roughness, shape, etc. of the channel. S is the slope. This is the slope or the steepness of the mountainside locally, so the flux rate will vary with the slope, and if the flux is constant, then there's going to be some sort of balance between the slope and the height. If the slope gets higher, steeper, then the height will go down, and that makes sense because if things are flowing faster, you don't need to have it as high. The constants m and k are simply that, constants. These are derived empirically, they're engineering constants, and for our purposes, we're going to assume that m is equal to about 1/2 and k is equal to about 3/2. Those are units that the engineering community has found, and so we know m and k, so we can use, we know m and k. Now what we need to do is decide what is the correct value to use for C, and that again has been determined by studying past Lahars, and what we find that for Lahars, C is typically in the range of about 8 to 50, and for our purposes we'll use a value of about 10. So we will assume a value of about 10 for the Chezy constant for Lahars. So now we have two equations. This one that is equation 2, which relates the flux to the steepness and also to the height. And then we also have this equation here, which reflects the height and the flux in terms of conservation of mass. So with those two things together, we should be able to solve this. What do we know? Well, we're going to know S, we can observe that. We can measure that off the mountain. We can measure X. We can measure that. We can assume Q. We can assume how big the Lahar is, and then based on that, we can solve for the height at any one time and its position. And so that's the next thing we're going to need to do, is learn how to relate these two equations, because what we eventually want to do is get some measure of the height as some function of time and position. And so that will be our goal, and in the next tutorial we'll talk about how to get from those two equations to this equation, which will be a measure of height versus time and position.